Welcome to the Explainer. Today, we're diving into one of my favorite tools from multivariable calculus, the change of variables theorem. It's a powerhouse concept, the kind you'd find broken down in a great textbook like Marsden and Tromba's. And honestly, it feels like a secret weapon. It lets us solve problems that seem completely impossible by doing something pretty radical, just changing our point of view. So let's kick things off with this wonderfully grumpy quote from the physicist Lord Kelvin. He actually called the vector a useless survival, which is just so ironic because we are about to unpack a vector-based method that is so powerful, so elegant. It's basically a mathematical superpower. Sorry, Kelvin.
Our adventure begins where so many great math stories do, with a really, really nasty problem. You know the type. The kind of problem that makes you look at it and just think, nope, no way.
Okay, so here's our mission. We need to calculate a double integral over this thing. It's a parallelogram, sure, but it's slanted and trapped between four different lines. Trying to set up the limits of integration for this guy, it would be a complete mess of splitting it into different regions, just a total algebraic nightmare. And that really brings us to the big question, right? When you're staring down a geometric beast like this one, what do you even do? You could try to brute force it, but that's just asking for mistakes. There's gotta be a better way. We need to think differently. We need to change the game. And here it is, the big idea. This is the genius move. Instead of fighting this difficult shape on its home turf, what if we could just warp the entire space it lives in to make our own lives easier? The whole idea, which is really the heart of Chapter 6 in Marsden and Tromba, is to create a transformation. Think of it like a map. It's a set of instructions that takes points from a nice, clean coordinate system, we'll call it the UV plane, and moves them over into our familiar, but in this case, messy XY plane. And check this out. Here's the strategy in action. We can actually define a specific transformation, we'll call it T, that takes this beautiful, simple rectangle from the UV plane and maps it perfectly onto our annoying slanted parallelogram in the XY plane. This is the key, because now we can just do our math on the easy rectangle instead.
But wait, hold on. It can't be that simple, can it? Of course not. There's a catch. This amazing simplification comes with a price. When you start stretching and twisting a coordinate system, you don't always preserve the area. And if we just ignore that, we are absolutely going to get the wrong answer.
This picture just says it all, doesn't it? We've got a transformation here that takes a simple square with an area of 1 and turns it into a rectangle with an area of 3. The area literally tripled. So yeah, we definitely need a way to account for this distortion. To solve this little distortion problem, we need a special tool. We need something that can measure exactly how much our transformation is stretching or shrinking the area at every single point. And that tool is called the Jacobian. Okay, so formally, the Jacobian determinant is the determinant of this matrix of partial derivatives. And I know it looks super intimidating, but trust me, the idea behind this scary-looking matrix is actually incredibly simple and intuitive. This is the magic ingredient that makes the whole technique work. The best way to think about the Jacobian is as a correction factor. It's the price we have to pay for simplifying the shape of our region. It is the ultimate stretch factor that tells us exactly how to adjust our calculations to get the right answer. And this is really what's going on underneath the hood. When our transformation takes a teeny tiny little rectangle from our simple UV space, it turns it into a teeny tiny parallelogram in our XY space. The absolute value of the Jacobian at that exact spot tells us precisely the ratio of those two little areas. It's a local stretch factor. So now we have all the pieces of the puzzle. We have our difficult region, we have our transformation to a much simpler region, and we have the Jacobian to correct for any distortion. So let's put it all together with the magnificent change of variables theorem. What's great is that the theorem gives us a super clear 4-step recipe. It's foolproof. Step 1. Spot the nasty integral. Step 2, find a good transformation that simplifies it. Step 3, calculate your Jacobian stretch factor. And finally, step 4, rewrite the whole integral with your new variables, multiply by the Jacobian, and solve. Easy. All right, enough theory. Let's see this thing in action. It's time to go back to that monster parallelogram from the beginning and watch this whole problem just dissolve. I mean, just look at this. On the left, that's the integral we started with. A complete and total mess. And on the right, after we apply the theorem, It's an easy-peasy integral over a simple rectangle with constant numbers for the bounds. The transformation turned an impossible problem into one that's not just solvable, but actually elegant.
And after all that, the crazy geometry, the warped space, the Jacobians, what's the final answer to this terrifying problem? It's just 1, the number 1. All that complexity, all that work, and it simplifies down to 1. That, right there, is the power of this method.
So why does all this matter? I mean, this isn't just some cool math party trick. The change of variables theorem is the fundamental reason why other coordinate systems, like polar or cylindrical or spherical coordinates, even work for integration. It gets used all the time in physics, in engineering, in computer graphics, anywhere you have a complex problem that needs simplifying. But at its heart, it's just a beautiful mathematical statement about the power of changing your perspective.
And that kind of leaves us with a final thought, doesn't it? We just saw how literally warping our view of a mathematical space made a hard problem easy. It really makes you wonder, what other complex challenges, in science, in art, maybe even in our own lives, are just sitting there waiting for the right change of perspective to become simple? Thanks for watching.